Now what we're going to do is look at some of these rational functions in inequalities. What you're going to find is that it's almost exactly the same thing as you're going to do with those polynomial inequalities. And basically because the same properties of dealing with positives and negatives carry over from multiplication as division. So for example, if I have a positive times a negative, I get a negative, and I have the same rule here. If I have a positive divided by a negative, I get a negative. And similarly, if I have a negative divided by a positive, I know that that's a negative. The same thing, like two negatives multiply to give me a positive. Well, same idea. A negative divided by a negative is going to give me a positive. I get the same outcomes. So I can use really the same logic in dealing with rationals. Basically factor and then just deal with the small factors because they're very manageable. So yeah, start by factor. Factor everything. Again, being kind of nice to myself, I didn't give a horrible challenging factor from section 2.2. These are both pretty manageable. So the top, I want two numbers multiply to -10, add to -3. So it should be x minus 5 and x plus 2. And the bottom is a difference of squares. And so the roots are x and 4. And so yeah, we should get something like this. And it's worthwhile to note right now what we've got. I don't want to call them all zeros because they're not. So what I've got is my top zeros, which are the actual zeros of the function, are going to be at 5 and -2. And my bottom zeros are, again, the ones that just come from the bottom, are -4 and 4. So we're going to list all of these zeros in our table. Because if the bottom changes sign, the whole thing changes sign. So we need to keep track of both where the bottom can change sign as well as where the top can change sign. So we need all of them. And so yeah, draw up a table. I'm gonna write my numbers here. So in increasing order, I'll have -4, -2, 4, and 5. And I'm going to list out all of the factors, including multiplicity. I don't have any multiplicity on any of these factors, so I don't have to worry about it. They're all to the power of 1. So I can just write them all out. All right, so I've got all of my zeros, top and bottom. I've got all factors, top and bottom. And again, if there were multiplicity, I would need it. And, oh, I didn't want that. Again, notice that I left myself a little gap on the left of the -4. Basically, if you have 4 zeros, you should have 5 columns. Always have one more column than your zeros. So you need everything to the left of that number and everything to the right of the 5. So it should represent, if you've done this correctly, the entire real number line, and those 4 numbers are just breaking it up. And so we can, yeah, just kind of use what we know about these, like these functions. They're all very simple lines. They're increasing, so they start in the negatives, and then they flip positive when they hit their 0. So x minus 5 flips positive at 5. X plus 2 flips positive at -2. X plus 4 flips positive at -4. and x minus 4 flips positive at 4. So on the other side of 4, I'll write positives, and then 4 negatives will all cancel and leave me with a positive. 3 negatives, 2 will cancel and I'll have 1 left over. 2 negatives are a positive, 1 negative is negative, 4 positives are a positive. And so I do have to be a little bit careful about my answer here. So for greater than or equal to 0, again, I'm going to break this into greater than 0 and equal to 0, because we do need to be careful. Greater than 0 just means positive. So I can just take my positive regions and list those. So greater than 0 is going to be negative infinity to negative 4, combined with, I might need to erase some of this. Combined with the second region, negative 2 to 4, and then combined with 5 to infinity. And the equal 0, so this is where I want to be a little bit careful. This should only come from the top. And the reason is the bottom zeros, if I plug in 4 to this expression on the left, I don't get 0, I get undefined. If I plug in negative 4, I get undefined. So it's only the top zeros that make the expression equal to 0. And so that's only 5 and negative 2. So I'll say. And so what those two numbers are going to do for me, they're going to close up those two intervals, the 5 and the negative 2, so I can use that. And then that allows me to write out my final answer in one nice big chunk. So the greater than or equal to 0 will be a negative infinity up to 4 but not included. And then negative 2 inclusive to 4. And 5 inclusive onwards. And so that should be my answer set there. So really the only difference that you have to look for these rational inequalities is just be careful about the endpoints. Yeah, with the polynomials, if it's strictly greater than, then they're all open. If it's greater than or equal to, then they're all closed. But with these rationals, if I include that greater than or equal to, unfortunately, you have to think a little bit more about which ones are closed and which ones are open. Now, if you are taking calculus and you'll be doing a lot of these calculations, all of your inequalities are strictly greater than or strictly less than, so you don't really need to worry about it. But it's valid enough for me to ask you that much right now. So we are going to do one more rational example, which will be a little bit trickier. Okay, so the second example that I'm going to do, so what you'll notice here is that I've got an inequality. All the other ones that I've done so far have had a 0 on the right-hand side, and this one doesn't. So your first instinct when dealing with these rationals might be that you can do some of the things you can do with equations, but we do have to be really careful about that. So let's say we plow forward, and I'm going to write this all in red to kind of emphasize that this is not what you really want to do. So let's say we plow forward, we cross multiply like we know that we're allowed to do with equations. And so what we'd end up getting would be actually x plus 3 over x, times x plus 3 is greater than x over x times x plus 3. So just kind of like finding the common denominator, however you would want to go about that. So I guess I actually haven't cross multiplied here. I'm sort of using a different technique. I'm actually finding the common denominator. So right now I haven't actually changed anything. I've multiplied the left side by 1, and I've also multiplied the right-hand side by 1, so I haven't done anything. But then you look at this and you're like, okay, I've got the same denominator, so basically I'm just comparing the top. So we'd have x plus 3 is greater than x. And then you look at this and you're like, well, yeah, x plus 3 is always greater than x. So you might think for this, then that your answer is all real numbers. It's always true. But then let's try a number. Let's say, well, first of all, let's try like x equals -1. So on the left side, what we're going to get is 1 over -1, which is -1. And on the right side, we're going to get 1 over -1 plus 3, which is half. And basically what we're saying right now is -1 greater than a half? Well, no. It's certainly not. So that is a little bit weird when I'm trying to tell you that all real numbers make this statement true. But obviously this one doesn't. What about x equals 0? Well, the left side doesn't even exist. So how can we compare that at all? So there's definitely a little bit of a problem. So if I look at what I've done on the left here, what I can see is that this step is actually okay. And I pointed that out. All we've done is multiplied the left side and the right side by 1. So that step, that is an acceptable step. But the logic that's going on in this next step is actually a bit bad. So I'll say this here. And the reason is because of problems with inequalities when you do multiplication. So it's certainly not always true. I'm going to put a big X through that because it's definitely incorrect. So just remember with inequalities, if I have this inequality, we could say -1 is less than 2 is less than 5, right? You believe me, I hope. If we take this whole thing and then multiply it by, let's say, -2, and we write this out, so I'd have a -1 times -2 is 2. 2 times -2 is -4, and 5 times -2 is -10. What you should actually see here is that the direction of all of the inequalities change when we multiply by a negative. And so what's coming into play here is to get from this step to this step, you're sort of multiplying away by this x plus 3. And the problem with that is there are x values, or there are places where this could be negative. And if that's the case, it's going to mess up our inequality entirely. So we don't want to do that because it makes it a lot more complicated. So we want to kind of take a step back from a lot of the work that I did there because it didn't make sense. So yeah, what we're going to want to do, and I'm going to just completely start over. In general, we always probably want to get an equal 0 on the one side of any of these, so polynomials or rationals. Doesn't really matter which side you force it, whatever you feel more comfortable with. But we're going to do that by subtracting one thing over to the other side. So I'm going to do 1 over x minus 1 over x plus 3, and now say that this should be greater than or equal to 0. And then I'm going to do kind of what I did on the left here. I'm going to combine them over the common denominator. So my least common denominator, which should be x times x plus 3. So I'll have x plus 3 over x plus 3 minus x over x plus 3 is greater than 0. If we have polynomials like this, we don't have to do any combinations, but we do here. So we should have x plus 3 minus x over x plus 3 is greater than 0. The top cleans up a bit. It actually ends up just being 3 over x plus 3 is greater than 0. And so with this, now I'm in a good position to actually go ahead and make my table and do the inequality just like anything that I've seen before. So I'm going to get rid of all this super wrong stuff that I wrote on the left here. So I've got, there's no top zeros. Because it's just 3, and the bottom zeros are at 0 and -3. So those are the only things that are going to go into my table. -3 and 0. I'm going to put the 3 there just because it's something that's in the function. It's not really going to matter. If it was negative, it would be really important. But it's just good for the sake of having all your components. And so 3 is always positive. X is negative until 0. And x plus 3 will be negative before -3 and positive after. And so we should get positive, negative, positive. And so basically the idea here is that this inequality is the exact same thing as this inequality. So greater than 0 means positives, and that should give me my solution set. So I'll have a negative infinity to -3 combined with 0 to infinity. And it's a strict inequality, so I don't have to worry about any endpoints or anything. They're all going to be outside of it. So yeah, if you don't have the 0 on the one side, it's a little bit more work to deal with, and you'll have to play around with it a little bit. Just be really careful in dealing with the rationals that you don't try to just wipe out denominators, because you're going to be applying multiplication that you're not quite allowed to apply. So you have to be a little bit more careful with it and just keep them there the whole time, like I've done on the right side here.